Good morning, everyone. I'm going to be talking about different planning analyses that are emerging and developing today that really look at how do you do planning for high penetrations of distributed energy resources. I'm going to build on some of the things you've already heard. I know Ben talked yesterday about DER forecasting. I'm going to build on that, talk about how that fits into load forecasting and the different uses of that. I'm going to talk about hosting capacity. I know Kevin spoke about some of that yesterday. I'm going to talk about more different methodologies and some particular examples from Excel where they've employed hosting capacity analyses. And then I'm going to talk about locational net benefit analysis and how you set yourselves up for the non-wireless alternatives that Lavelle just presented. So all this stuff is really, it's new, it's evolving, we're still comparing methods and benchmarking. So things haven't completely settled out yet. We're still feeling our way through these processes. So Carrie, if you go to the next slide, and actually the next slide after that, as you know, DERs can impact system cost and reliability. And not just at the distribution level, but also at the bulk power system level. For example, you may be aware in California, there's 8 gigawatts now of distributed PV. California, CalISO is a 50 gigawatt peak system. So you can imagine 8 gigawatts of distributed PV that the CalISO can't really see it. They don't have visibility into it. They can't talk to it, they can't communicate with it, and they can't control it. So to have a significant part of your system be a resource that you can't see, communicate with, or control makes system operations very difficult. So you can imagine what that does in terms of them trying to manage their duck curve, because they also have another 12 or 13 gigawatts of utility scale PV. So if they need to curtail PV, and they do, in the shoulder months, on a regular basis in the middle of the day, especially on weekends, they've got to curtail the utility scale PV. Also, most of the rooftop solar, it's optimized for customer economics, not for utility services. And they may not be providing, well, they aren't providing ancillary services. And because it's optimized on customer economics, it means it may not be helping the grid with what the grid needs, but rather just providing the maximum amount of energy. Finally, the CalISO will tell you that in the late afternoon, they have trouble actually maintaining that really fine system balance between generation and demand. That's reflected in their NERC control performance standard scores. That's an operational reliability issue. Okay, so you talked yesterday about the impacts on the distribution system, and those impacts are very specific. It depends on the DER, it depends on the location, it depends on the feeder loading, and some of that we're going to get into in this presentation. So Carrie, if you go to the next slide. Currently, most of us are in a reactive mode when it comes to managing DERs. So this may not be a big deal if you've got a little bit of DER in your system, but if you've got increasing and fast growth of DERs, it can become a mess. Customers don't have good information, so they make decisions about DERs based on their own economics, which might not align with grid needs. The utilities have to manage the integration of the DER, and if the interconnection is difficult, the location perhaps is not a good location, it may be an expensive interconnection. In the end, no one might be happy with the whole process. Michael Coddington, I think, mentioned that if the next DER pushes the feeder over some tipping point in terms of reliability, and it requires some feeder upgrade, that next customer is responsible for that cost, even though that upgrade might enable many more megawatts of customers installing DERs, of their neighbors. You probably already know about the battles between utilities and DER developers regarding what's the value that DER brings to the system, you know, whether the DER compensation is shifting costs to other ratepayers. So there's a lot of controversy around some of these things. Carrie, if you go to the next slide. So proactive planning is a way we can clean up this mess. So we can harness the significant services that DER provides that the grid needs at the right time, at the right location, and we can get third-party investment to do it. So how do we get to the point where we're providing information to customers about what the grid needs and where and when, and then incentivize that or somehow solicit their participation? So I'm going to talk about load and DER forecasting, which helps resource planners determine, you know, what really needs to be built after you take into account all of the rooftop solar, the electric vehicles, the demand response, the energy efficiency, and then bringing that down to a feeder level to help you determine, you know, maybe you want to prioritize these feeders because they're going to get stressed first. Prioritize those if you're going to start upgrading equipment on feeders. And instead of the back and forth that you have today between someone who wants to install DER, but they don't have information about how easily they can interconnect, and then the utility who's got to do a bunch of different studies to determine the viability and the options for interconnection, we can proactively put the information out there and guide developers or third parties. And through hosting capacity analysis, we can basically tell you where DER can be interconnected more easily and likely more cheaply. And then locational net benefit analysis, that can inform, on the one hand, where you might get a bigger bang for the buck in terms of a non-wires alternative that could offset a traditional upgrade. And then on the other hand, it could be used to help inform compensation or inform programs or incentives that you might want for different types of DER. Carrie, if you go to the next slide. So we need to be able to forecast load, accounting for DERs, in order to conduct our resource planning, so we know what we need to build and we don't overbuild. And also, if you know that you're expecting, for example, a lot of distributed solar, you need to think about that in your resource planning process. This links to what Joe talked about earlier in terms of integrated resource planning, because you might need to think about storage, or you might need to think about other flexibility options to help manage that PV, or maybe you won't build as much utility scale PV. So all of this needs to fit together with your traditional resource planning process. And then you also need to know about DER growth so we can properly do our distribution planning processes. We've got a poll now to just sort of see where folks are at in their DER forecasting currently. So the question is, to what extent do your utilities forecast DERs? And Carrie, I'm assuming that you're just waiting for half the people to respond?
Yep. And we're almost there, just a few more.
Okay, so it sounds like people in this region are actually doing quite a lot of DER forecasting, so that's excellent. Okay, so can we go to the next slide? I'm now going to talk about load forecasting with DERs, and I'm going to start with a high-level view. This is from Con Edison, and what it shows is kind of from a high-level view, what are the big things that you take into account? And we've already kind of discussed this, but I'm going to take a deeper dive, so I'm going to just show this one more time. So you take your historical peak loads, And this is showing the current year. Let's say the current year was a little cool, and we expect next year to be warmer. So you do a weather adjustment. That's the dark blue with the light blue bar added to it. You account for your macroeconomic and growth drivers, population growth, economic growth, and that's the gray bar. And then you account for new loads. So you've got electric vehicles. In Con Edison territory, there's a lot of steam to electric AC conversions. And there you've got, say, some peak amount of load that you're planning for. And then you've got the things that subtract off the load. And so your demand side management includes your demand response and your energy efficiency and demand management programs in orange. Then in pink, you can see your distributed generation. So that's your PV, your rooftop solar, your combined heat and power, your storage, and you end up with the green, the forecast for a future year. And so that's the general framework, and it's pretty obvious how that works, and it looks pretty simple. If you go to the next slide, Carrie, this table, and you don't have to read it all, but it just gives you an example of the data that goes into one piece of that last graphic. So this is just the data that goes into the PV forecasting, the distributed PV forecasting in California. And the idea here is that you've got a lot of disparate sources organized differently, different assumptions. This one might be organized by zip code, and that one might be by feeder or distribution planning area. So a lot of work goes into creating some kind of consistency from this and some consistent scenarios from this. And what we're trying to do, is understand the key impacts on load from, PV, electric vehicles, or things we might be incentivizing like energy efficiency and demand response. And then we got to break all that down into a really granular level in time and in space. So, if there's a lot of PV growth, I want to know where is that happening, which feeders and where, maybe on the feeders. If there's a lot of electric vehicle growth, I want to know, is it a level 2 charger or is it a level 1 charger? And, when are they charging these things? Because all that's got to feed into this load forecasting. So if you go to the next slide, Carrie, one of the important things is we used to just look at peak. We now have to look at hourly profiles. We really need to look at hourly profiles during the day and maybe 8760 throughout the year. Previously we had conventional dispatchable generation, so you could just focus on peak. Also, load used to be better understood. Now we've got things like, variable electric vehicles. And again, if they're on a fast charger, that's increasing the demand of a facility potentially by a lot. So with variable output from DERs and variability and load increasing, we need to really look at hourly profiles. What the top right graphic here shows is that peak is moving, and people might have talked about this yesterday. I didn't attend all of yesterday, unfortunately, but this is for New England, and it's showing with increased solar on their system that they're expecting that peak is moving from 5 o'clock to 6 o'clock to 7 o'clock as that solar kind of provides energy and pushes that peak outward. The bottom left-hand graphic shows one of the reasons why we need to look at hourly profiles on a feeder basis. So this bottom left-hand graphic is from PG&E. And let's say this particular feeder is limited by its ability to handle reverse power flow. So that top yellow line is showing the load profile, and we can't allow the distributed generation to exceed that. Carrie, if you go to the next slide, these arrows are pointing to different points in this graphic, where the first arrow shows, let's say I've got a distributed generator like a small hydro plant, operates 24/70. I'm constrained by that minimum load. It can only be up to 0.4 megawatts. So I've got PV, I'm constrained by that next point where the blue hits the load line, and we can accommodate 0.65 megawatts of PV. And if I have storage, and you look at that 4-hour storage light blue line, you can see that I can accommodate much more, 0.9 megawatts with that particular feeder. So if you were just looking at peak, you would lose a lot of accuracy in this process. If you go to the next slide, Carrie. I know that Ben talked a lot about DER adoption. I don't want to be redundant. I just wanted to point out really just one finding from PG&E that I think is useful. We look at historical behavior to try and predict future behavior. In some cases that works, in some cases it doesn't work. This is a finding from PG&E when they did their distributed PV forecasting. And what they found on the left-hand graphic is showing residential PV interconnected in 2013 on the x-axis and 2014 on the y-axis. And each point here is a specific substation in their territory. And the idea here is that, it's kind of following on a straight line. Basically, the idea is that past behavior predicts pretty well future behavior for residential PV. The right-hand graphic, though, is for non-residential PV. And what you can see here is that there's not really as much correlation. So past behavior not being indicative of future behavior. So I just thought that was something, there's a lot that goes into these models and analyses. And you've really got to do a lot of disaggregation to understand what's going on. Okay, if you go to the next slide, Carrie, I'm now going to talk about a specific example from National Grid. So the typical methodology for this, as I showed earlier, and I think as others have said previously, is we look at all of these different components and then we aggregate them. So in order to take historical load and use that as a starting point, you've got to sort of take out all of those components. So they reconstruct their historical load by, trying to disaggregate what was the impact of energy efficiency programs, demand response programs, how much PV did we have on our system, how much storage, how much electric vehicles, and pull out those signals to that, to the load. And again, you have to use hourly profiles because all that stuff is variable during the day or variable during the season. And then you independently create forecasts for energy efficiency for your distributed solar, for your demand response, your storage, your electric vehicles. And then you independently do what you used to do to determine load growth. And then you can construct from all of that, aggregate it for a net load forecast. So this graphic here is showing for National Grid, this is up in the state of New York, Niagara Mohawk, and the dark blue trace that's a little volatile there are the actual peak demand. So their all-time peak was back in 2011 at 7 gigawatts. Last year, it was 6.4 gigawatts. But last year was a cooler year than normal. And over the last 20 years, it was considered like in the 23rd percentile, so warmer than 23% of those years. So they look at the last 20 years and they do a weather-adjusted basis and they adjust it to normal. So if you adjust it to normal, or average, that would adjust up that 6.4 megawatts to 6.7 megawatts. So Carrie, if you go to the next slide, there's the actuals, which is the dark blue, and then there's the weather adjusted, which is the, I guess they're triangles, or maybe they're diamonds. It's a little hard to see. Now there's a couple other uncertainty bands that I'm showing here. So when you do your planning, do you plan on events that happen 1 in 2 years, or 1 in 10 years, or 1 in 20 years? Right, so those other lines here are depicting those uncertainty ranges. So again, that blue is weather normal or average, 50-50, 50% of the years are higher, 50% of the years are lower. that's what they're planning for on a sort of system basis. But that pink line, the next line up, is showing 1 in 10 years. So that's the 90th percentile. And that's the kind of planning uncertainty band that they use for transmission planning. And then the orange line, if you can see the dotted orange line at the very top, that's the 95th percentile. So that's 1 in 20 years. Now, when they do planning on the distribution system, there's less diversity. So they use that 95th percentile. Another thing I just wanted to point out, this is the peak hour that I'm showing here, but peak changes, as I mentioned earlier. So this peak hour, at first we're showing 5 to 6 p.m., but in the later parts of this graph, later in time, that peak hour is actually shifting out to 6 to 7 p.m. and then 7 to 8 p.m. because you've got the distributed solar and the electric vehicle growth. Okay, so Carrie, if you go to the next slide. So this slide shows the load forecast and the DER forecast. So again, they've broken it down to energy efficiency in blue, PVs in green, electric vehicles, a little sliver of green on top. There's a little sliver of blue on top, which is demand response, and a little sliver of purple, which is storage. So the dashed line on top is showing that if you don't account for DERs, you're expecting 0.2% load growth. When you do account for DERs, the load growth, so the net load growth is that heavy, solid line with circles. It's basically flat, maybe slightly declining. And you can see that when you get out to the end of this 2029, the DERs are decreasing peak load by almost a gigawatt. And if we go to the next slide, Carrie, I also just wanted to anticipate a question that might happen. You might be wondering what's happening with those green PV, step changes in their forecast. What's happening here is that the peak hour is shifting. And when that peak hour shifts, the PV is providing less contribution to that peak hour. Okay, Carrie, if you go to the next slide. So in reality, each of those pieces that I showed on the last bar chart all have a lot of uncertainty, right? We don't really know how much PV we're going to have in the next 10 years. We don't really know how fast EV growth will occur, or if there's going to be cheap gas all of a sudden and people don't want to buy electric vehicles. So in reality, you want to have different scenarios for your different DERs. And what they used was a low scenario, high scenario, and a base scenario for each DER. So if you do the combinatorial math, you get 243 different cases, and then they've got 3 weather scenarios for each of these, so that's 729 cases. That's shown here. So you can sort of see the ranges that they're getting with this with these different scenarios. And Carrie, if you go to the next slide, by the time you get out to 2034, there's over a gigawatt of uncertainty between the highest and lowest scenarios. So that's something to think about in terms of, when I do my resource planning for centralized resources, what do I need to build out? There's a lot of uncertainty out there. Okay, Carrie, if you go to the next slide. Now, there's also the daily, the hourly profiles to look at. We don't want to look at just the peak. We also want to look at what that hourly profile looks like. And this is showing the hourly profile on the peak day. And it helps to understand the impacts of DERs. And in the future, this is going to be really important. For example, there might be a lot of storage on our systems in the future, and you need to know, are you going to be able to charge that storage sufficiently? Are you going to have sufficient duration for that storage? You're not going to get a sense of that by looking at peak. You're going to need to look at hourly profiles. So these 2 graphics, the one on the left is showing 2024. So it's showing the different scenarios for 2024, and you can see that they're pretty tight, right? We have a lot more certainty about what's going to happen 4 years out. The right graphic shows that when you get 10 years past that left graphic, there's a lot more uncertainty, right? So the different colors are showing all the different scenarios, and there's a significant range of what might happen in that future, at that future time. So Carrie, if you go to the next slide, in the biggest range is, there's a big range at peak, and there's a really significant range in the middle of the day. What's load going to be like? And again, this has all kinds of implications on what you're going to be doing in your traditional generation resource planning to make sure you can operate with this kind of a system. You know, can you accommodate that very low midday net load? That's something that CalISO struggles with in the spring. Okay, Carrie, if you go to the next slide. So what I just showed was the DER rolled up to the system level for National Grid. What National Grid needs, though, is DER forecasts down to each substation and feeder in order to do the kind of analysis I'm going to talk next. And so I think Ben talked a lot about using demographic data and historical information that feeds into how you disaggregate all of that load. In the case of National Grid, they use GridLab-D. It's an agent-based model that helps them with developing the granularity of these forecasts, and it incorporates technical and financial and market adoption considerations and all of that. Okay, Carrie, if you go to the next slide. I just include this in here as some of the questions that you might think about as your utilities are going through these types of processes. And Carrie, if you go to the next slide. So I'm going to switch gears now, and I'm going to talk about stuff that's a little bit more electrical engineering focused. This is hosting capacity or integration capacity analysis. So hosting capacity is how much DER can I put onto the system without adversely impacting power reliability or quality under the current configurations of the system. So before I do any mitigation, before I do any upgrades, how much can I put on here and still have a reliable system? This is a model-based calculation. So this is an approximation of the potential adverse impacts of DER on the distribution system. And when people talk about hosting capacity, they might say, you know, I've got, 1.2 megawatts, or they might say I've got, 50% of the peak loading of this feeder, or they might give you a range. At 1.2 megawatts, I know I can handle it. At 1.6 megawatts, I know I can't take anything, and in between, it will depend. At this point, Carrie, do you want to put the poll up? So I just wanted to get a sense of how hosting capacity might be used in your region.
I'm going to give it one more second to let a few more folks get there. We're almost at 50%.
Okay. Okay. All right, so most folks aren't sure if this is being done. And some folks are saying that they're not doing hosting capacity yet. So this is a forward-looking analysis. Again, it's an emerging analysis. It's something that you need to think carefully about. Whether when's the right time to start doing this. Again, this is going to be about informing customers and the distribution planning process, maybe streamlining interconnections, improving operations. So the first use case is to really help developers, provide them guidance so that they know which locations are going to be easier to connect to and potentially a lot cheaper to interconnect to, and which ones might take a lot more time and money, resources to interconnect. And heat maps are what we typically use to provide that information. Carrie, if you go to the next slide. Another potential use case is streamlining and potentially automating the interconnection process. So a lot of utilities have, for example, a fast track screening process. And if your project doesn't make it through that screening process, you then go into a supplemental review process that's a little bit more detailed. And if you don't make it through that supplemental review process, you then go into a detailed interconnection study. And of course, that takes up, there's a bunch of engineering time and a bunch of money that goes into doing that interconnection study. For a lot of applications of DERs, the hosting capacity analysis and the maps are sufficient and efficient proxy for the screens that utilities are using today. The California PUC, their use cases for this process are interconnection streamlining and also distribution planning. So Carrie, if you go to the next slide. So for distribution planning, such as where you might proactively upgrade the grid or where you might want to prioritize certain grid modernization investments first, hosting capacity can provide you with information to help you with that. Or you could use hosting capacity analysis to show you why, maybe DER growth is going to be unlikely to occur in some location because the grid can't handle it. So Carrie, if you go to the next slide. The last one of these is something that's a bit more futuristic, even for the places that are doing this in earnest today, and that's dynamic hosting capacity. So Lavelle just talked about reconfiguring feeders, for example. You can imagine that the hosting capacity would be different depending on how that feeder is configured. So depending on how that feeder is configured, you might be able to host a different amount of DER at that time. So there might be some real-time operational use of hosting capacity in the future. But the basic way to think about hosting capacity is, you've got, some screening process. It's really fast. It's not that accurate. Utilities conduct detailed interconnection studies. It takes a lot of time and money, and it's very accurate. And hosting capacity kind of gives you that middle piece. It gives you some level of speed and some level of accuracy, and it can be proactive. Okay, if you go to the next slide, Carrie. One of the things to think about in undertaking hosting capacity analysis is that you need a good amount of data and assumptions that go into this. Again, it's a big modeling effort, and you need to have accurate models of your feeders. Where are the loads? How big are they? What kind of loads? How does that loading change over the course of the day? How does it change over the course of the seasons? If you've got SCADA data for your substations and feeders, that's great. National Grid, the utility that I just showed in the last section, 70% of their substations and feeders have SCADA. They can get their hourly load profile data, their interval data from that. But the other 30% of their substations, you have to go in and manually read. They have analog meters and, a little plastic indicator, and you kind of reset it. And then, when that meter goes up, it kind of gives you what the peak is, and you go in and manually read that, at some regular interval, maybe every month. So depending on what your particular system is, you'll have different amounts of data. The data is important because, it informs thermal loading, so thermal overloads, also voltage profiles. And it's not just a matter of where the loads are, what kind of load? Is it a lot of induction motors that are going to consume a lot of reactive power? And so understanding all of this is going to be important. You know, you've got some equipment out there that helps you regulate voltage, but do you know the field settings? Do you know the schedule? Maybe it, you know, runs at this schedule in the evening and this schedule, you know, in the middle of the day. Or are you going to make assumptions about these things? And then grid configuration is another piece of this. Do you know how this may get reconfigured, and that feeds into these analyses as well. So if you go to the next slide, Carrie, these are the power system criteria for hosting capacity. So LaBelle just showed, you know, a list of some of these different criteria and what some of the actual, you know, for example, ANSI limits for voltage are. But the general categories that we're looking at for power system criteria are thermal criteria. That's about overloads on transformers and conductors. Voltage, so that's about, you know, making sure we keep voltage within those ANSI limits. Protection, that's about making sure that your protection devices, your relays, your fuses, your reclosers all operate as they're designed, and that they can protect the areas that they are designed to protect. For example, that first box that says relay reduction of reach is something that a lot of people don't kind of intuitively understand, but the idea is that protective relays cover a certain region, sort of in a certain location. And if you've got PV that's downstream from that area, that may be masking some of the current and causing that relay to actually be protecting a smaller area than it should be protecting. And then reliability issues. Of course, we talked yesterday that we don't want to have unintentional islands, and we also want to be able to have the ability to reconfigure feeders when we need to. So if you go to the next slide, Carrie, I think Kevin discussed this yesterday. We don't know where the DER is going to go. So in this case, I'm looking at a feeder in the Southeast, and this is from a study that GE did a couple years ago. And on this particular feeder, you know, see it's sort of a, you know, it's very organic looking. It's not like the beautiful feeder that Barry showed you yesterday. But there's 4,000 to 5,000 nodes in this feeder where PV could be interconnected. If you go to the next slide, Carrie. This is showing the voltage profile of that same feeder that I just showed. And the left-hand side is showing the substation, and then as you get away from the feeder, that's going off to the right. And you can see voltage is going down, right? There's resistance in the lines, voltage, and people are using the energy. Voltage is dropping as we go through that feeder. You can see that they prop up the voltage to close to the ANSI high voltage side at the substation because they know the voltage is going to drop as you go through the feeder. You can see about in the middle of the feeder somewhere, voltage sort of gets propped up all of a sudden. So there's some device, maybe a capacitor or bank, that's helping to provide reactive power to increase the voltage there. This is the profile for when we have zero PV on the system. If you go to the next slide, Carrie, this is the same feeder, but with one big PV plant at the end of the feeder, and you can see you've exceeded the ANSI limit at the end of the feeder. You go to the next slide, Carrie. I'll show you the part that exceeds the ANSI limit in red. Okay, so that's with a single PV, that's 20% of the peak loading of that feeder. If you go to the next slide, Carrie, here we've taken that same amount of PV and just sprinkled it across the feeder. And now you can see the voltage profile stays within the ANSI limits. So where you put the PV makes a huge difference. and how you run these kinds of analyses and how you assume this makes a huge difference. If you go to the next slide, Carrie, there's several different types of hosting capacity methodologies, and they vary in terms of what their use cases are, in terms of how much data you need, in terms of how long it takes to run them. Of course, you're going to have questions about accuracy, and there are a few comparisons about accuracy, but it's just a few at present, so it might be a little premature to be real conclusive about that. The first method, I'm not going to talk about these in great detail because I'll worry that I'll run out of time, but first method is similar to what Kevin talked about yesterday, stochastic methods like a Monte Carlo method. Add lots of DER and lots of locations, run thousands of scenarios, give you a range of impacts. The second method, the streamlined method, this is something PG&E did in their first hosting capacity study, and it combines a limited number of load flow analyses with a bunch of equations and algorithms that helps you do the analysis really quickly. The iterative method, this is what the 3 IOUs in California are now using. This simulates sort of what an interconnection study does. You use your traditional distribution load flow modeling tools. You know, you add to one node increasing steps of the DER and look for violations. Then the last one is there are hybrid methods, the most popular of which is EPRI's Drive. And this is a tool that a lot of utilities are now using that can sort of take some of the different aspects of the other models and combine them to make something that runs quickly, but still gives you a little bit of that iterative answer, but with a sort of stochastic approach. Okay, if you go to the next slide, Carrie, I'm going to give an example of Xcel Energy. So they did a hosting capacity analysis in 2019, building on a previous analysis in 2018, and they used that EPRI Drive tool, and they modeled about 1,000 feeders. They made a lot of improvements over what they did in 2018. I'm not going to go into those details here. I'll just maybe talk a little bit about the results. 129 of the feeders, of those 1,050 feeders, have 0 hosting capacity. A lot of them have over a megawatt of DER already. That doesn't necessarily mean you can't put PV on your roof if you're on one of those feeders. And that's because the model looked at 100 kilowatt increments on the 3-phase feeders. It didn't look down into what's happening on the secondary that my house is connected to. But you know, if you wanted to put a 1 megawatt solar garden on that feeder, that would be a problem. On the other side of that, if a feeder does have a lot of hosting capacity, you really have to look into the queue and see how much DER is, you know, ahead of you, because those projects ahead of you may use up the existing hosting capacity. They did a really nice case study sensitivity analysis on one feeder. And then the thing I want to talk about next is the mitigation options analyses on the feeders that had 0 hosting capacity. So Carrie, if you go to the next slide, this just shows what the heat maps look like and the bubble. Carrie, if you go to the next slide, I want to deep dive into the mitigation analysis a little bit. So they had, from their last year's study, 95 feeders that had 0 hosting capacity. They used a new tool that EPRI developed that helps them kind of walk through and streamline what an engineer might do in a mitigation analysis. So look at different ways you would mitigate the different problems. So for overvoltage, maybe you adjust the power factor setting on the resource itself or on other resources nearby. You could also reconductor. Now, I note that the costs of these two things are very different, and the costs for the different mitigations are different. what they tried to do was to look at low-cost options that would free up a lot of hosting capacity. If you go to the next slide, Carrie. So this shows the violations that they saw in those feeders. So first of all, of the 95, one of them was a mistake, so they actually ended up with 94. And many of the feeders had multiple violations. And this is similar to that whack-a-mole problem that Kevin talked about yesterday. You might fix this overvoltage problem, but then you gotta fix the reverse power flow problem next. So that's something you need to go and mitigate for each feeder. If you go to the next slide, Carrie, this shows the result. So I probably don't have a huge amount of time to go into this in great detail, but the left side is showing that when they addressed their voltage and their thermal problems, they were able to free up a good amount of hosting capacity in many of their feeders. So 15 feeders, they couldn't really do much with. It was just the mitigations needed were just too much. But for 77 of the feeders, they were able to get at least 1 megawatt and up to 10 megawatts of additional hosting capacity open on those feeders. And what was the cost? The right-hand chart is showing the cost. They were able to so there were no zero cost feeders, but they were able to do a significant number of feeders for under, I forget what this is, $300,000. And so 53 feeders for under $300,000 per feeder. So that's showing you an idea of what some of these costs can be. The costs go up to $3 million for some of the reconductoring jobs on some of the more difficult feeders. Okay, if you go to the next slide, Carrie. These are some of the considerations that you might want to think about if you do take the path of doing hosted capacity analysis in your region. If we go to the next slide, Carrie, I'm going to now switch gears, get away from the electrical engineering stuff, and talk about locational net benefits. So a lot of what I'm going to talk about here is preparing for the non-wires alternatives that Lavelle just mentioned. And Carrie, I think we have a poll here. So I wanted to get a sense of how non-wires alternatives are considered in your region. Okay, so seems like the use of non-wires alternatives is somewhat limited. So this is a new area that folks are looking into. Again, the idea here is that DERs can provide a lot of benefits, and let's point them to where they can really help the grid the most, and really save us a lot of money. And that's what we're going to talk about in this next session. So thanks. So locational net benefits analysis is about, what's the value of providing a service at some specific time, at some specific location. And there's different things you can use this value for. One is it could inform compensation. Maybe you want to do a value of solar tariff. And so you want to know what the value of solar is so that you can set that tariff. Maybe you want to incentivize some new program for demand response, or maybe you want it to feed into rate design. One of the things I'm going to dive into a bit more in this talk is going to be the non-wires alternatives piece of this. So what are the traditional things that a utility would otherwise do? What are those costs, and what's the suitability of a non-wire alternative? And let's develop projects around those needs that non-wireless alternatives are really well suited to provide, and hold a solicitation and have third-party providers come in and provide those solutions. So if you go to the next slide, Carrie, this first 3 slides just talks a little bit about that first piece in terms of informing compensation. So, the value stream of traditional generation is shown on the left, and that's really straightforward. You got energy, you got capacity, you got ancillary services. And then when we think about the value of distributed generation, so the middle set of bars, you can add to that, well, I'm offsetting transmission and distribution losses, I'm providing some hedge against some risk. And then when you really get into the locational piece of that, and that's on the right, you can add to all of the things in the middle the fact that you can defer perhaps a distribution upgrade or provide some other service specific to the distribution system at that particular place. In calculating these kinds of benefits, if you go to the next slide, Carrie, it seems like it ought to be straightforward, just add each of these components. It's actually not as straightforward as it seems, because there's a ripple effect of the different value streams. So when you actually do go through this, if you were to calculate some amount X of distribution losses, that actually helps to offset some amount Y of transmission losses associated with that. And then a generator avoids producing, energy plus the transmission and distribution losses. And maybe you need less capacity to serve that. And it's not just the capacity, depending on how your rules for planning reserve margin are. It might be another 15% less capacity because let's say you've got a 15% planning reserve margin. So all this to say, it gets a lot more complicated, and you need to be aware of these ripple effects. So Carrie, if you go to the next slide, this is an example of what that value stream might look like. This is rooftop solar in Colorado Springs for different levels of distributed and utility scale PV. It's important to note that if you're looking at things like this, especially for rooftop solar, incremental megawatts of rooftop solar have less value as you add more and more solar, because you're providing all this energy at the same time, and you're moving peak out to later in the evening, so contribution to capacity is also decreasing as you increase those penetration levels. Carrie, if you go to the next slide, I'd now like to talk about a process, do a deep dive into a process that PG&E is going through with the other IOUs, SoCal Edison, San Diego, and California. So the CPUC established a distribution investment deferral framework. And what you do in this framework is you've got a grid needs assessment and a screening that leads to distribution deferral opportunities, identification of those non-wireless alternatives that you can then solicit for. So what does the process look like? You use some of these components that I talked about already. PG&E establishes a load DER forecast and disaggregate that DER and load forecast down to each substation and each feeder. And then they do technical studies and ensure that the system can operate under normal and abnormal conditions. If there's a problem, like there's an overload on a specific circuit, they need to identify that need. When is that going to happen? Which hours does the problem occur? And this grid needs assessment, it takes the form of a big spreadsheet that they submit to the PUC, and from that grid needs assessment, they develop projects from these needs. And one project might be able to address multiple needs, and these are their planned investments. Then they look at, from these different planned investments, they screen them. Can DER help with the problem? Do they have time to do a solicitation? And they end up with some candidate deferral projects that then they prioritize. And they use different prioritization metrics that I'll describe. And then they can go out to bid with the top projects from that. So if you go to the next slide, Carrie. So in the PG&E example for their grid needs assessment, they identified about 7,000 different grid needs. And again, they're telling you, where is it? Is it, a voltage support issue, a reliability issue? Why do they have a need? Is it that demand is growing? What's the deficiency in terms of megawatts or in terms of reactive power? When is the date that that's going to be needed? And then if you go to the next slide, Carrie, this sort of breaks down those 7,000 projects, or 7,000 needs, sorry, not projects, 7,000 needs into different categories. So the first category refers to distribution capacity and overloads on equipment. The voltage support is keeping that voltage within the limits, the NC limits that have been described. Reliability services improve reliability in a specific location during an outage. So this refers to the reconfigurations that Lavelle just spoke about. When you've got an abnormal operating condition and now you're feeding the feeder through some back tie. And then resiliency is microgridding during outage conditions. So that would be actually being able to do a standalone microgrid. And I'll just note, yeah, there's 0 here, and this was done before those power shutoffs that happened in the fall. That kind of thing might be changing in the future. So, a lot of these were around voltage support. A lot of these got screened out because the need was prior to 2022, and there's timing requirements as part of the screens, because it takes some time to issue a solicitation and go through the contracting process. They winnowed all of this down to, and a project can support more than one need. So they winnowed all this down to 18 candidate deferral projects. And then, Carrie, if you go to the next slide. Then, when you've got these candidate deferral projects, you need to figure out, okay, which ones am I going to address first? Right, all 18 would be a huge amount of work, and it's not clear you even have people to respond to that kind of number of solicitations. So you need to prioritize. What are you going to do first? And this is a qualitative prioritization methodology. So they're using high, medium, low. And the 3 buckets of priorities are cost effectiveness, forecast certainty, and market assessment. So the first one, cost effectiveness. So you look at the cost of a traditional upgrade. You turn that into a locational net benefit number by looking at the maximum kilowatts needed during the deferral period. And so take that unit cost, amortize it, and turn into $1 per kilowatt per year. And then you also turn into $1 per megawatt per year, where you look at the maximum megawatt hours needed during any one year. So with those metrics, the idea here is that if you've got something that would otherwise be really expensive, it provides a lot of value. The second one is forecast certainty. The idea is, how certain do we know we're going to need this? So obviously, if it's in a couple of years, we're pretty certain. If it's many years out, we're not as certain. If we've got SCADA data and we can really demonstrate from the SCADA data that we've got a need, that's more certain than trying to apply some sort of rules of thumb to load profiles and things like that. The third piece is market assessment. How likely can DER be successfully sourced to fit this need? So what you look at here are things like projects that I can give a day ahead notification, right? So I'm going to know a day ahead, and I'm going to, give you a phone call or a text message in the day ahead to respond. That's more likely to be successful than something where I have a real-time need. So day ahead projects get ranked higher, and then real-time projects get ranked higher of something called real-time islanding, which is sort of capacity that's got to be maintained independent of PG&E service. How often am I going to need to call on you? How many days per year? And when I do call on you, how many hours is that going to be? Is it going to be 5 or 10 or 20? How many grid needs are there on a circuit? Anyway, so all of these things play into how they rank things, and engineering judgment and experience play into all of it. Again, this is qualitative. They start with numbers, but then they get to high, medium, low. So if you go to the next slide, Carrie, this is just showing an example of the grid needs assessment. So, for example, the one that's highlighted here, CalFlex Bank 2, it's got a day ahead need. So, I'm going to know that I'm going to have a problem 1 day in advance. It's got a 4.8 megawatt need. It's a summertime need, so I know I'm going to have a problem during May to August. 92 calls per year, so I'm anticipating I run into this problem 92 times a year. What are the hours? 4 p.m. to 8 a.m. So that's a 16-hour duration. That's really long. We don't necessarily have cost-effective, battery storage that I could put in there that's going to help manage the 16-hour duration. So, there will be things like that you might flag as difficult to meet with a non-wires alternative. And this is similar to what Lavelle just showed in the Excel assessment, but maybe a little bit more of a process and a little bit more with some quantification behind, the engineering judgment. So if you go to the next slide, these are the candidate projects. I mentioned there's 18 of them, 83 megawatts of candidate projects. This is the list of them. And I mentioned they did high, medium, low in terms of their assessment of these prioritization metrics. So blue is high, purple is medium, red is low. And then they broke them down into tiers. There's a few things to note. For example, this FMC one, the fourth one down, it's got a red flag on it. It had a red flag, and they initially didn't put it into their top tier because the red flag was because it was a real-time project, not a day-ahead project, and they thought it was going to be difficult for DER to do that. On the other hand, it had really good cost-effectiveness. You can see that by the blue bar there. And they need to start getting experience with real-time projects. So they put that one into the tier 1, to one of the ones that they want to go out for solicitation with first. Red flags are things like, if you look at this Estrella substation, the first one in tier 3, it's got a red flag because the in-service date is actually beyond their planning period. And there's a lot of grid needs and a lot of hours per call. If you go to the next slide, this is sort of the data that goes into the ultimate judgment call about how to prioritize different candidate projects. So again, if it would have cost a lot to do a traditional upgrade, it gets a higher ranking. If you're pretty certain of your forecast, your need is near term, and you got SCADA, it gets ranked higher. And then if you think there's a good market of current DER technologies to address the need, then it gets ranked higher. Okay, if we go to the next slide. So these are some of the considerations that you might want to take into account if you are having your region look at locational net benefit analyses and working through a process like this. And then, Carrie, maybe we can just go to the next slide, which is resources. Number of resources and links. There's a huge amount of information. If you just go to the last slide, Carrie, feel free to contact me if you have questions, because I couldn't put all the resources on there, and there's a huge amount of really good stuff. So are there questions?
Yes, thanks, Debbie, so much. That was terrific. I have a question for you. Most hosting capacity analyses that utilities are doing are for distributed solar only. And in California, as you discussed, the 3 large investor-owned utilities are including other distributed resources like storage. Can you talk about the value of including storage in these analyses in tandem with distributed solar?
So I think that it is important. It depends on your area and what you see happening. I live in Colorado, and here there's a huge amount of rooftop solar, a huge amount of electric vehicles, and people are really interested in behind the meter storage, and there is a growing amount of that happening. So it is starting to happen in more places, and I think it's important to start getting ahead of the curve, because as I mentioned, all of these things have an impact on your system. And even though, if you think about it, like storage has a really good grid-friendly aspect in that it's helping to manage, all the variability of the solar, for example, right? So it's grid-friendly, and you think, oh yeah, there's not really a negative impact. Well, that's not necessarily true. These things actually, they do have impacts on protection, for example, like that whole thing that I just mentioned about relay reduction of reach and inverter-based resources like PV, like battery storage, providing different fault current, and therefore your protection devices might not see the same area they used to see, and they see something less, and they're protecting something less, and you need to go and mitigate that. So, so they do have impacts, and we do need to start thinking about those impacts. I think the electric vehicles are probably the bigger thing to really worry about, because I got an electric vehicle. It doubled our peak demand. It doubled our electricity use. It's a huge amount of, we have a level 2 charger, so that makes a difference. But, if everyone on my feeder gets an electric vehicle and it does this to their electricity use, that is a huge impact. The distribution system is not going to be sized to manage that. So it's, I think you got to look at what's happening in your region and anticipate and be proactive.
Thanks, Debbie. And I think just one more question. You mentioned that some utilities are going forward with non-wires alternatives for some distribution projects, even if they cost a little bit more than the traditional distribution system, in order to get experience, so long as they meet other, needs like timeline, engineering requirements, and so forth. So can you give us a sense, like, at least, where you've been working, how much above the traditional, the cost of the traditional projects are these non-wires alternatives going in these kind of pilot situations?
Oh, actually, I didn't say that. I might have misspoke. So if you just go back to that slide, which one is it, 52? I might have misspoke if that's what folks heard. So what I was trying to say is that the top 3 projects on here, PG&E had put into their top tier 1 category to go forward with. The 4th one, they had not initially, and the reason was it was a real-time project, and they didn't think DERs could do that very well, or they weren't sure that would work out real well. And one of the reasons they pushed it up is because it was so cost-effective. Actually, if you go to the next slide, 53, you can see it's listed in here, and it's got really good benefits. You know, the cost of that traditional upgrade is very high, and so having DER come in and provide the service could save them a lot of money. And so this is actually a case where they were going to save a huge amount of money, but they weren't sure if the DER could do it. And they wanted to try and get some experience with, let's try to see how this works out, having DERs respond in real time. But as for, can you do this just to get experience with it? I mean, there's a lot of value to doing pilot projects to get experience with them. Although, you do try to pick the ones that are going to provide you the biggest, bang for your buck, the ones that are going to offset as much as possible traditional cost.
Thanks very much for those clarifications. That was really helpful.
Thank you so much, Debbie, and thank you all for participating and sending in your questions.